Good morning, everyone. Thank you for joining my presentation today. I'm Min-Feng from the Department of Information Management at National Taichung University of Science and Technology in Taiwan. Today, I'll be presenting our research on an open-source approach to automated threat intelligence in IoT, a comparative study of Wazuh and commercial EDR solutions. This work was conducted in collaboration with my colleagues Yung-Hui and Jian-Zhi Chen. Our study addresses a critical challenge in today's rapidly expanding IoT landscape: how to effectively secure resource-constrained devices using cost-effective, automated threat intelligence solutions. Let me quickly outline what we'll cover in the next 15 minutes. We'll start with the problem statement and research objectives, then discuss our methodology and experimental setup, followed by our key results and performance comparisons, and finally conclude with our findings and future work directions.
The Internet of Things has experienced unprecedented growth across all sectors. We're seeing billions of connected devices deployed in everything from smart homes to industrial control systems. However, this rapid proliferation has amplified serious security concerns. Traditional security solutions face significant challenges in IoT environments. These devices are inherently heterogeneous, ranging from simple sensors to complex embedded systems. They operate under severe resource constraints with limited processing power, memory, and battery life. Most importantly, there's an urgent need for automated and scalable threat intelligence solutions that can adapt to this diverse landscape. The challenge is clear. How do we protect billions of resource-constrained devices without breaking the budget or overwhelming their limited capabilities?
Let me elaborate on the specific problems we're addressing. IoT environments are notoriously difficult to secure with existing commercial solutions due to three main factors. First, device heterogeneity. We're dealing with everything from Windows 10 IoT devices to Linux-based Raspberry Pi systems, each with different architectures, operating systems, and capabilities. Many IoT devices simply cannot support resource-intensive commercial security solutions without impacting their primary functions. Third, and perhaps most critically, there are limited cost-effective and adaptable approaches for automated threat intelligence collection in these environments. Commercial EDR solutions, while effective, can be prohibitively expensive when deployed across thousands or millions of IoT devices. This creates a fundamental tension between security needs and practical deployment constraints. Our research addresses these challenges through three primary objectives. First, we aim to develop an automated threat intelligence collection and analysis system specifically designed for IoT environments, based on the open-source Wazuh security platform. Second, we wanted to evaluate the effectiveness and efficiency of this open-source approach through comprehensive comparison with 5 leading commercial EDR solutions. Third, we sought to provide a thorough analysis of the strengths and limitations of open-source security solutions in real-world IoT deployments. These objectives guided our experimental design and evaluation framework. Our research methodology follows a systematic empirical approach. We simulated real-world IoT environments using 2 of the most commonly deployed platforms, Windows 10 IoT and Raspberry Pi, running within virtualized environments to ensure controlled and reproducible testing conditions. We conducted comprehensive attack and malware simulations using industry-standard tools to evaluate detection capabilities under realistic threat scenarios. Most importantly, we performed direct comparative analysis with 5 leading commercial endpoint protection solutions: Sentinel-1, Cortex, Sophos, Fortinet, and Threat Sonar. Our methodology involved 4 key phases. First, setting up the IoT environment simulation. Second, deploying both Wazuh and commercial EDR solutions. Third, conducting systematic attack and malware simulation tests. And fourth, analyzing detection capabilities and performance data across all solutions. Our experimental infrastructure was built on Proxmox VE, providing a robust virtualized environment for IoT device simulation. This allowed us to create consistent, controlled testing conditions while maintaining the resource characteristics typical of actual IoT deployments. We deployed Wazuh and each commercial solution across both Windows 10 IoT and Raspberry Pi platforms, ensuring comprehensive coverage of the most prevalent IoT operating environments. To ensure accurate performance assessment, we integrated Telegraph and InfluxDB for continuous monitoring of system resource usage throughout all testing phases. This gave us precise measurements of CPU utilization, memory consumption, and system impact across all evaluated solutions. Our testing framework employed 3 industry-standard tools to ensure comprehensive threat coverage. First, Atomic Red Team, based on the Meter ATT and CK framework, allowed us to simulate real-world attack techniques across different platforms. We tested 19 Windows attack techniques and 17 Linux attack techniques, covering the full spectrum of common IoT attack vectors. Second, Hydra enabled us to execute systematic brute force attacks against RDP and SSH services, testing each solution's ability to detect and respond to authentication-based attacks that are particularly common in IoT environments. Third, Malware Bazaar provided us with diverse real-world malware samples, including MSI installers, executable files, and shell scripts. This gave us insight into each solution's malware detection capabilities across different file types and attack vectors. This comprehensive testing approach ensured that our evaluation covered both technique-based attacks and actual malware threats that IoT devices commonly face. Now, let's examine our key findings. The results were quite remarkable, and in some cases unexpected. Wazuh achieved 100% detection coverage on both Windows and Linux environments, significantly outperforming all commercial solutions. Commercial solutions range from just 26.3% detection rate for Sentinel-1 to 68.4% for Fortinet in Windows environments. In Linux environments, the range was 29.4% to 70.6%. However, this superior detection came with trade-offs. Wazuh demonstrated higher false positive rates, flagging some benign system behaviors as potential threats. This highlights the importance of proper tuning and configuration in production deployments. Interestingly, commercial EDR solutions provided better out-of-the-box brute force attack blocking capabilities, while Wazuh required manual configuration of the active response module to achieve similar protection levels. One notable finding was that technique T1574, hijack execution flow, was the only technique successfully detected by all evaluated solutions across both Windows and Linux environments, suggesting this is a well-understood and consistently addressed attack vector. Perhaps most significantly, for IoT deployments, Wazuh demonstrated superior resource efficiency with the lowest average CPU usage at just 4.63 among all tested solutions. This is crucial for resource-constrained IoT devices, where every percentage point of CPU utilization matters. In contrast, some commercial tools like Sophos showed much higher resource consumption, potentially impacting performance on low-power IoT devices or affecting their primary operational functions. Our 5-year total cost of ownership analysis revealed dramatic differences. Even when including hardware and operational costs, the open-source approach demonstrated significant cost advantages over commercial alternatives. For organizations deploying security across thousands of IoT devices, This cost difference becomes substantial and can determine the feasibility of comprehensive security coverage. This cost effectiveness is particularly important for IoT deployments, where the sheer number of devices can make commercial licensing costs prohibitive, potentially leaving devices unprotected due to budget constraints. Let me summarize our key findings and their implication. Wazuh's strengths are clear: superior detection coverage at 100%, the lowest resource utilization at 4.43% CPU usage, and significant cost advantages over commercial alternatives. These make it particularly attractive for large-scale IoT deployments where cost and resource efficiency are paramount. However, there are important trade-offs to consider. The higher false positive rates require careful tuning and ongoing management. Manual configuration requirements mean organizations need sufficient technical expertise. We also identify specific detection gaps, particularly with MSI-based malware and certain shell scripts. Based on these findings, our deployment recommendations are nuanced. Wazuh is well suited for non-critical IoT environments where cost effectiveness and broad coverage are priorities. However, commercial EDR solutions remain preferable for high-security environments and critical infrastructure protection, where the cost of false negatives outweighs the benefits of cost savings. In conclusion, our research demonstrates that the Wazuh open-source system offers practical effectiveness for IoT automated threat intelligence. The combination of superior detection coverage, exceptional resource efficiency, and significant cost advantages makes it a viable alternative to commercial solutions for many IoT deployments. Looking ahead, our future work will focus on three key areas. First, enhancing detection capabilities, specifically for MSI and shell script malware, where we identify gaps. Second, integrating machine learning approaches to reduce false positives and improve overall accuracy. Third, exploring hybrid deployment models that combine the cost effectiveness of open source solutions with the specialized capabilities of commercial tools. Our research contributes a practical evaluation framework and deployment guidelines that organizations can use to make informed decisions about IoT security implementations across diverse environments. Thank you for your attention. I'm happy to take any questions about our research methodology, findings, or implications for IoT security deployments.